Hello and welcome to this revision video for ESS IB, and today we're looking at topic 1.2, which is focusing on systems and models, or in some cases models of systems. So the first part of this, we're going to look at models and systems. We're then going to look at the three different groups of systems, and then the case study that you should have studied, which is the Gaia theory, which is a model of a system. So just to look at the specification of this and what you actually do need to know going forward, well, you need to know the idea that systems approach can help the study of complex environmental issues. So, for example, the understanding that the Earth is a closed system helps us study global climate change and our understanding of the greenhouse effect. You need to know that the use of systems and models simplifies interactions but may provide a more holistic view without reducing issues as a single process. So the idea is models might help us understand things a bit better, and systems may help us understand it, but we know systems link together. So you need to understand what system is, you need to know what properties of certain systems have, you need to know about inputs and outputs of energy and matter, and you need to know how we represent systems in diagrams and the different types of systems. So what is a system? Well, a system is a set of interrelated parts that work together to make a complex whole. So, a system is a way of visualizing, therefore, a complex set of interactions. Systems can be of any scale, so it could be a bike, for example. It could be the Earth itself. And systems can be what we call open, closed, or isolated, which we'll look at more in a moment. And it is materials and energy can enter and leave systems, and they may undergo transfers and transformations within a system. So, for example, a bike, the energy that goes into a bike is from the human to the bike would be chemical energy going in, and then obviously the bike is kinetic energy, but then heat energy would leave the bike as the friction is caused. And examples might include systems like food chains, and in these systems where the food enters the ecosystem, the sunlight enters the ecosystem, so energy comes in, materials are transferred from one system to another, because a producer could be a system, a consumer could be a system, and then energy leaves as heat, or matter is recycled. Matter and energy can also be stored in a system, and that is generally represented by a rectangle. So you can see matter here would be stored in this nutrient pool or in the decomposers because it's represented as a rectangle. Energy movement is normally represented as a triangle, as an arrow, sorry. Most systems may be stable, so they might not change, or they may be dynamic and change over. There are three systems that make up the biosphere, the Earth. So the Earth is Biosphere or Biosphere 1, and the systems are the air, which is the atmosphere, the rocks, and the hydrosphere, the water. And those systems interact with each other, and materials move from one to another, and energy also moves from one to another. So they would be open systems. Now we're going to be talking about models, and a model is a simplified version of a real thing. So a model may be a simplified version of a system, which helps us understand how a system works, what changes to a system may cause, and the rules that make a system, because all systems do follow rules as to what affects them. And the image here is of Biosphere 2, which was a model of the Earth, and it had several biomes, so the desert area, a ocean area, a mountain area, and all those different areas were interlinked together to study how the Earth could survive and see where we could create a artificial closed system. And it helped us understand the Earth in many ways, as we'll look at now. So there are different types of models. It can be a physical model. So an aquarium is a good example of a physical model. It could be a wind tunnel, where we study artificial recreations of wind. and Biosphere 2 was an physical model of planet Earth. It could be a software model, so that could be looking at climate change models, predicting climate change in the future, or James Lovelock's Daisy World, which I'll be mentioning in a few minutes. It could be mathematical equations, and it could be data flow diagrams. So why do we use models? What are the advantages? Well, the advantages are that models are easy to work with. We can use them to predict impacts of change. We can apply similar findings to similar situations, so we can predict how something will affect a similar situation in another area. We can use it to help identify patterns, and it can be used to be scaled up or scaled down in some cases. But the disadvantages are the models can be too simplistic, so we may not actually realise everything we need to include in the model. Accuracy can be lost because it's not to the same scale. If your assumptions are wrong, if you make some wrong ideas and you put stuff into there that is wrong, the model will become wrong, and predictions may be inaccurate. And this was seen with Biosphere 2. So Biosphere 2 was a model of Biosphere 1, which was Earth, and they built in Arizona in the 1980s. Several people were locked in Biosphere 2 with the aim of being self-sufficient for 2 years. And they had to be released after a certain amount of time because, unfortunately, they didn't produce enough food to meet the needs of the participants, and the oxygen levels got too low, and they needed to be oxygen needed to be let in, which meant it was no longer a closed system but became an open system. Now, these issues were because we didn't understand enough all the complex interactions of the real biosphere of Earth. So it's too simplistic. We assumed we understood how it worked, and we found out problems that didn't. That did later help us because it made us realise how interdependent on other species we are. Now, scientific developments as a result of this have continued, however. So whilst Biosphere 2 at the time was considered a failure, it actually has become a really important area of scientific understanding, because now we can carry out huge ecological studies in different biospheres, and it has become one of the world's biggest ecological laboratory. And we have looked at it and we have used it to predict and study the effects of coral bleaching, which we now see happening in the real world. And now it's being used to focus on soil behaviour and looking at how flooding is impacted by soil types and the behaviour of water moving through soil. So one model of the Earth which has got a lot of fame to it and has been generally accepted is the Gaia theory, or the Gaia principle, which was created by James Lovelock and then supported by another respected scientist, Lynn Margulis. And the Earth, what James Lovelock said, is that the Earth is actually a planet-sized organism which regulates itself through negative feedback. And whilst this may seem a bit far-fetched, actually, if you think about it, think about human. If we get too hot, we cool ourselves down through sweating. If we get too cold, we shiver and warm ourselves up. That is negative feedback. It's reversing a change from the optimum conditions. The Earth does the same thing. The Earth has a constant temperature, and when the sun is, this Earth's temperature stayed constant even though the sun is giving more energy out than it used to. The composition of the atmosphere is stable even when oxygen should technically react with all the other elements and decrease, but it doesn't. And ocean salinity is always about 3.4%, even though salt levels which are entering via rivers and erosion from further rivers should increase that salinity. It doesn't do so. So the Earth is a planet-sized living organism, called James Lovelock, and those factors make the Earth a stable organism. The Earth regulates its own temperature. And James Lovelock has been able to suggest and use this model of the Earth being an organism to predict how the Earth will change in the future and to explain how the Earth works. Now, one thing he came up with was an explanation, well, how does the Earth maintain its inhabitable conditions? So this was created by James Lovelock and Andrew Watson, and it explained that the Gaia theory didn't actually require an intelligent planet, but only feedback loops. And actually life itself was what kept the planet within safe limits. And this DAISY World program basically is a computer simulation, and what it shows you is that it depends on what life is there as to how hot the planet is. So in this very simple simulation, Lovelock suggested that there was two types of plants on the Earth: black plants and white plants, or black and white daisies. Black plants absorb loads of heat energy, white daisies reflect loads of heat energy, and as a result they can maintain the temperature of the planet. So what it shows here in the simulation is that the sun, as we know it is gradually getting warmer, because over billions of years the sun's reactions change and the sun is emitting more heat. So the Earth should get hotter as a result. So in the early Earth, the sun in this model was releasing very little energy, which we know is true, and the only life that could exist were the black daisies, because they absorbed more temperature. Then because they absorb more heat energy, the temperature then went up and the planet becomes warmer than it would be if the daisies were not there. So you can see here two lines. We've got the luminosity of the sun, how warm it's going to be, and here is what we get if the daisies are present. They're absorbing all that heat energy, and here if the daisies are not present. And the temperature of the Earth should really be between 10 and 30 degrees for it to be habitable. Over time, a mutation occurs, and white daisies evolve because they outcompete the other ones. And the reason they outcompete the other ones is the white daisies reflect heat. So as the Earth's temperature starts to get high, and you can see here with just black daisies, the Earth temperature hits a peak just below 30 degrees, starting to get too warm. The white daisies are able to survive because they reflect the heat. That causes the temperature of the planet to drop, because it reflects a lot of the heat back out into space, and so more survive than if they were just black. This reflection of heat therefore regulates the planetary temperature. And then over time, the mixture of white to black daisies can maintain the heat of the Earth and the temperature of the Earth because of the heat reflection or absorption. And you can see it maintains it within that range much more than if there was no life on the planet, even though the sun is getting hotter and hotter and hotter. So you need to know the different types of systems, and the three types of systems are: firstly, open systems. This is when energy and matter can be exchanged, and whenever you're talking about the systems, you need to refer to both of these things in the answer. So open systems where energy and matter can exchange the system boundary. Most ecosystems interact, okay, and therefore they are open systems. So this island, for example, energy will come in the form of sunlight, which will be captured by the plants for photosynthesis, and then that energy, which is then chemical energy, some of it will go into the water, for example, and that as leaves and debris from the forests, and that then will be passed into the aquatic ecosystems. So that is that. Birds might fly by, they might produce feces, and then those birds then are adding maybe nutrient matter to that ecosystem. So a question that often comes up is explain in much detail why a forest is an open system as possible. So a forest is an open system, and these are just some of the answers you could have, because plants fix energy from light in photosynthesis. Nitrogen from the atmosphere becomes fixed into the soil bacteria, which then can be absorbed by leguminous plants, and then that introduces nitrogen into the food chain. Carbon dioxide is fixed and converted to glucose from the atmosphere in photosynthesis, so it comes out of the atmosphere into the solid material of the plant and to the biomass. Herbivores might move, they might eat some of that material and move to like close grasslands and then take that matter with them when they produce feces, leave that matter there. And soil minerals might get eroded, they might go out via a stream. Transpiration might mean that the water is lost from the plant's leaves and it goes into the atmosphere as steam. And then rainwater may also move from the atmosphere into the soil, which can be absorbed by the plants, and heat can obviously enter via sunlight. So all these things show that energy or matter is coming in or leaving the ecosystem. A closed system is where energy can be exchanged, but matter cannot. So again, you must mention about the matter is not exchangeable in this case. Now, they are rare in nature, but the different systems and the different cycles that you'll have learned, so the carbon cycle, the nitrogen cycle, the water cycle, are all closed systems because they don't interact with other systems and they're more isolated. The biggest example, though, is you actually know the Earth is a closed system because the Earth gains energy from the sun, and some of that sun energy, that is infrared radiation, radiates back into space. Now, the key thing with the Earth is that obviously matter isn't entering or leaving. Now, obviously, we do take the assumption there that nothing's doing that. We obviously have invented spaceships and rockets that can leave the atmosphere, and occasionally asteroids and comets do enter. But on a consistent basis, they don't. So we say it is a closed system. And a closed system helps explain the Gaia hypothesis, the fact that it has to be a closed system for this to work. Otherwise, these factors wouldn't be able to be balanced if we couldn't have some heat entering the Earth and some heat leaving the planet. And therefore, an isolated system, the last one, is when no matter or energy can leave the system, and there is no natural examples of this, but the example that you are expected to know is that the universe is an isolated system, but don't worry about going into detail as to why you're only expected to know the universe would count as an isolated system, because no matter or energy goes beyond the universe. So what would you be expected to know? Well, you should be expected to know that these are the effects. Basically, an open system does allow energy and matter to be exchanged. A closed system does allow matter, but closed system does allow energy, but no matter to be exchanged. And an isolated system does not allow either to leave. Hopefully that gives you all the information you need about systems and models.